IQIs and penetrameters are one of the most misunderstood parts of industrial radiography. Their job is not to measure defects. Their job is to prove the radiographic technique had enough sensitivity to reveal discontinuities if they were present. This becomes a code compliance issue under ASME, AWS, and other fabrication standards. In this module, we are covering source side placement, film side placement, shims, step wedges, and why geometry matters more than people think. One of the biggest mistakes rookies make is assuming the IQI somehow sizes flaws or proves weld quality. It does not. An IQI only verifies radiographic sensitivity. In simple terms, it proves the exposure technique could reveal a certain level of detail. If the IQI is unacceptable, the radiograph itself may be invalid even if the weld looks clean. That is why inspectors care so much about IQI visibility, density, and placement. This is physics and code compliance working together. Source side placement is the preferred configuration whenever possible. That means the IQI is placed between the radiation source and the test object. This setup best represents total material absorption through the actual part thickness. Most fabrication codes prefer source side placement because it gives the most realistic indication of technique sensitivity. Film side placement is generally considered a fallback condition when geometry or access restrictions prevent proper source side placement. Sometimes source side placement simply cannot happen. Small diameter pipe, vessel internals, nozzle configurations, or restricted access may physically block placement. In those cases, the IQI may be placed film side. When this happens, a lead letter F marker is normally added to the radiograph. That marker tells the interpreter the IQI was positioned on the film side rather than the source side. Without that identification, the radiograph can become technically unacceptable under code review. Now let's talk about shims. Weld reinforcement changes absorption and film density. Without a shim, the IQI may appear artificially sensitive because it is sitting beside a thicker weld crown or uneven geometry. The shim helps simulate actual material thickness, so the IQI sees conditions closer to the production weld area. In simple terms, the shim prevents the radiograph from cheating the sensitivity requirement. Good technicians pay attention to shim thickness because bad shimming creates misleading results. Separate blocks and step wedges are also used in some situations. These are common when direct IQI placement becomes impractical. The material used should be radiographically similar to the production material, and the thickness should reasonably simulate production geometry. The entire goal is maintaining representative absorption conditions. If the simulation is unrealistic, the sensitivity verification becomes questionable. General placement rules are straightforward but critical. The IQI should not obscure the area of interest. It should be placed near the weld and match thickness conditions as closely as possible. Inspectors also avoid unrealistic positioning over geometry transitions, backing rings, or abrupt thickness changes. Bad placement creates misleading sensitivity and can make a technically compliant radiograph operationally worthless. In the field, common RT problems repeat over and over. IQIs placed too far from the weld, wrong shim thickness, incorrect identification markers, density mismatches, placement over geometry transitions. All of these can produce technically bad radiographs even when the exposure itself looked acceptable at first glance. Experienced Level 2 and Level 3 personnel spend a lot of time catching these details before the customer does. Bottom line, IQIs verify technique sensitivity. Placement matters, shims matter, geometry matters, and code compliance still requires engineering judgment. Radiography is controlled physics, not magic.